Look inside a running engine and you will see a continuous sequence of violent detonations. Fuel is mixed with air and ignited under extreme pressure to force pistons down, generating the mechanical power that actually moves a vehicle. Containing thousands of continuous explosions comes with a massive physical byproduct: extreme heat. A large percentage of the energy from that burning fuel does not turn into forward motion. It turns into raw, radiant heat, soaking into the surrounding metal. If that heat is not removed instantly and continuously, the metal components expand beyond their engineered tolerances. Within minutes, cylinder heads warp, the crucial seals between the engine parts, called head gaskets, disintegrate, and pistons expand until they physically fuse to the cylinder walls, resulting in total engine seizure. An internal combustion engine is effectively a machine constantly on the verge of melting itself into scrap metal. It only survives because it is built with an active, highly engineered thermal management system. Keeping this machine alive requires solving a complex engineering problem. You need 4 things: a heat creator, a fluid to carry that heat, a component to release it, and a mechanism keeping everything moving. This diagram shows the physical loop that answers the problem. The engine block creates the heat. A liquid coolant circulating through internal passages absorbs it, and the radiator up front sheds that heat out into the passing air. Placed along this circuit is the thermostat. It acts as a temperature-controlled gate. When you first start the car, the gate stays shut, trapping the fluid near the engine so it can reach its operating temperature quickly. Once it gets hot enough, the gate opens, allowing the fluid to travel toward the radiator to be cooled. A passive loop has a critical flaw. Without physical force to push heavy liquid through these tight internal cassettes, the flow stalls completely. The fluid stops moving, and the heat stays trapped exactly where it was generated. The entire thermal matrix relies on a mechanical heart to force it into motion and prevent self-destruction. That component is the water pump. Before we look inside the pump housing, there's a common misconception. A modern car water pump does not circulate plain water. It pushes a specific chemical mixture of antifreeze and water designed to resist boiling, prevent freezing, and protect the internal metals from corrosion. The core of the pump is a rotating component called the impeller. Unlike a traditional plunger or piston, the impeller does not push fluid forward in a straight line. We can see the centrifugal physics at work in this top-down view of the impeller. As the curved blades spin, coolant particles enter the center hub and are violently accelerated outward. This outward motion creates a pressure differential, drawing more liquid into the center while ejecting high-pressure liquid out the sides. Shifting to a profile view reveals the power path. An external rubber belt is turned by the running engine. That belt spins a pulley on the outside of the pump, which connects to a solid steel shaft, spinning the impeller attached to the other end. This direct mechanical linkage takes the raw rotational energy of the engine and converts it into rapid fluid momentum, pushing the pressurized coolant deep into the narrow cooling passages surrounding the cylinders. The water pump uses the engine's own mechanical power to continuously flush lethal heat away from the combustion zones. This design creates a severe engineering conflict. You have a rapidly spinning metal shaft passing directly through a stationary metal housing, which is filled with highly pressurized scalding liquid, and it has to do this without leaking. Looking at this cross-section, you can see how manufacturers solve the friction problem. They place bearings around the shaft to allow it to rotate smoothly, and a tightly fitted mechanical seal to keep the fluid inside. Directly below the seal is a deliberate opening carved into the metal called a weep hole. When these components fail, the physical symptoms follow immediately. If the bearings wear out, the shaft begins to wobble, producing a distinct grinding or squealing noise. If the internal seal degrades, pressurized coolant slips past it and bleeds out of the weep hole, leaving a visible trail of fluid. There is also a silent circulation failure. Over time, the blades of the impeller can corrode or snap off. The shaft will continue to spin completely normally, but without intact blades, it fails to move the fluid. Because the pump's physical integrity contains the liquid, a compromised seal or a wobbling bearing rapidly depressurizes the system. A microscopic leak at the pump directly initiates a catastrophic engine meltdown. Traditional belt-driven mechanical pumps have reliably cooled engines for decades, but their physical design carries an inherent flaw. Their rotation speed is strictly tethered to the engine's RPM. If you accelerate hard, the engine revs high, forcing the pump to spin rapidly. This draws continuous mechanical energy away from the engine, even if the thermal system is already cold and does not actually require maximum fluid flow. To eliminate this mechanical waste, automotive engineers shifted to the electric water pump. Instead of relying on a physical belt, an electric pump operates entirely independently via a dedicated motor. This allows the vehicle's computer to dictate coolant flow based purely on exact thermal demand, completely ignoring how fast the engine itself is spinning. Decoupling the pump from the engine block refines the entire process. It turns engine cooling from a blunt mechanical reaction into a highly efficient, precisely controlled thermal management system. The pump does not actively cool the engine itself, and simply forcing fluid to move faster does not guarantee a colder engine. But the water pump is the high-stakes mechanical heart of the machine. It endlessly moves fluid, acting as the sole physical force maintaining the precise thermal balance required to keep the engine alive.